Okay, this lesson is 9.4. It's on improper integrals. So before we start, let me start with an example that will kind of lead into this, right? So if we had given you an integral 0 to 4 of 1 over x minus 3 squared dx, right? So when presented with a problem like this, what you would have done would be to use up this and say, all right, u equals x minus 3, du equals dx. Therefore, this is the integral of 0. Actually, you can change the numbers too. So u of 4 equals 4 minus 3, that's 1. U of 0, that would be 0 minus 3, that's negative 3. So negative 3 to 1, u to negative 2 du, right? And then so you say, all right, negative u to negative 1, evaluate negative 3 to 1, so that's negative 1 over u. Evaluated negative 3 to 1, that's negative 1, minus negative 1 over negative 3, so minus 1 over 3, which is negative 4 over 3, right? But, okay, so first of all, area can be negative, totally fine. But if you were to graph this function, 1 over x squared, x minus 3 squared, you would see that this equation looks something like this, where there's an asymptote here, and here is your function. First of all, my function is completely above the x-axis, so my area should be positive. Secondly, the region I'm looking at is from 0 to 4. So I'm looking at this whole thing, and it's going all the way up to infinity. So my area is not only is it not negative, my area actually doesn't end. It's going to infinity. So what we have here are improper integrals because our integrals involve infinity in one form or another. So if you take a look at the first examples here, these integrals all have infinity in their intervals, right? So whether it starts at infinity or ends at infinity, or it starts and ends at infinity, you would actually approach it like so. So we're going to give you ways and tips on how to approach an integral like an integral that involves infinity so that it is actually doable. Keeping in mind that infinity is not a number, right? Infinity is this endless, boundless entity. So you cannot treat it like a numerical value like we normally did, where we had an integral from negative 2 to 5 or negative integral from 3 to 4, right? So you cannot treat it like a number. And so whatever applied to integrals before with A's and B's, you cannot have the same application at this point. You are actually going to have to do something different, right? And remember, we can't reach infinity. We can approach infinity. So we're going to bring in the idea of limits again to help us approach that number because we can't actually be there, right? Okay, so two possibilities of an improper integral. One possibility is, as we saw in the previous example there, that the answer is infinity, right? Because the graph doesn't end, it's boundless, so it reaches to infinity. Another possibility is that the graph actually does something what we call converges. So you have a graph like so, and you have a graph that kind of goes down really quickly. It's decreasing really quickly. So even if I say, all right, I start here and I'm going off to infinity, because it's decreasing so fast, it is going to converge into a number, kind of like when you had geometric series back in trig or algebra 2, where you had these series where the ratio is smaller than 1, and eventually the ratio is decreasing your number by a set value that is going to fill in the blanks in a way so that if you're looking at it as a puzzle, you have a half and you add a quarter, you add a 1/8, you add 1/16, you add 1/32. So you're filling in the tiny pieces, the tiny crevices, so that eventually as it reaches infinity, it's going to fill in that hole, that gap. So you actually get a number at the end. You actually get a finite sum at the end, right? So this is another situation where you have, let's say this a value to infinity of f of x dx, because it equals a number, it equals a numerical value, this is a convergence, right? And then because the previous example, we are heading to infinity, we are looking at a divergent integral. So we'll talk more about this later on, but right now just kind of have an idea that these are vocabs to come, okay? All right, remember, we cannot have infinity as our bounds, right? It cannot be our interval. So what do? We use limits to kind of take care of that issue. So we're going to rewrite this as limit as t approaches infinity. This is integral 1 to t dx over x. And now you're only dealing with this right here because you know how to take the antiderivative of that. So deal with that first, and then we'll bring in the limit after, right? So you know the antiderivative of dx over x is natural log of x. You evaluate it 1 to t. Don't forget you still have your limit out here, right? So then we evaluate again, fundamental theorem of calculus, natural log of t minus natural log of 1. Still have my limit. And you can go ahead and plug it in. Your natural log of infinity minus natural log of 1. Natural log of 1 is 0. Natural log of infinity is infinity. So my answer is infinity. So this is a divergent integral because it's going off to infinity. Okay? All right. What about something like this? Okay, same thing. We're going to replace the infinity with limit as t approaches infinity, 1 to t, 1 over 1 plus x squared dx. Okay, you should recognize this right here. This is the antiderivative. This is the integral antiderivative of tangent inverse. So this is really limit as t approaches infinity of tangent inverse of x. You value from 1 to t, right? So go ahead and plug that in. You get limit as t approaches infinity. This is tangent inverse of t minus tangent inverse of 1. So this is tangent inverse of infinity minus tangent inverse of 1. So remind yourself of what the tangent inverse function looks like, right? A normal tangent function looks like this. A tangent inverse function is going to turn it, it's going to flip over the axis of y equals x. So it's going to look something like this. So you actually have asymptotes here and asymptotes here. So as tangent approaches infinity, it is approaching this asymptote of pi over 2. So this value is actually pi over 2. And tangent inverse of 1 is pi over 4. Therefore, my final answer is pi over 4 for this integral. Okay, again, kind of interesting because think about it. You're trying to go from 1 to infinity and it never ends, but it actually converges so that you get a final answer of pi over 4. Okay, all right, what about situations that was in our first example there? What about the fact that there's an asymptote? So this second type is not as obvious. The first type, you can see the infinity in your integrals. The second type, you have to figure out where your asymptotes are. Sometimes the asymptotes are at the endpoints of our integral, right? Sometimes the asymptotes are in between, in the middle of my integral. So you kind of have to know that, all right? So for the first one here, you have 0 to 3 of 1 over 3 minus x. So if you plug in the 3, right, if you plug in this endpoint, you will see that you get 1 divided by 0. Hence, you will have an asymptote there. So then you ask yourself, your interval is going from 0 to 3. We're going from this edge to this edge. I'm trying to get to this edge of 3, so I'm coming from the left side. So then you can rewrite this as limit as t approaches 3 from the left side, because that's to meet up at the end of my interval, right? So it's coming from the left side of 0 to t, 1 over root 3 minus x dx. Okay, so now I'm going to remind myself this I can do with u sub, right? So I'm going to do u sub there. I'm going to go u is 3 minus x, du is negative dx. I am going to remind myself that I'm going to move my coefficient over. So then the du equals dx. Now, because it's not a real u substitution, you really don't want to put the t into your u and then replace your interval. So what I would do is I would actually do the u sub integration right here and then bring back my x as my original function. So this now becomes negative u to negative 1/2 du. And so when I take the antiderivative, I get negative u to the 1/2 times 2. So this is really negative 2 square root of 3 minus x for this antiderivative, right? So you can actually do the whole thing and then now bring it back into your equation. Limit as t approaches 3 from the left side. And I have I already took the integral. So the integral is negative 2 root 3 minus x from 0 to t. Okay, now I plug that in. I get limit as t approaches 3 from the left. I plug that in, negative 2, 3 minus t minus a negative 2, so plus 2 root 3 minus 0, which is root 3. Okay, and now this is why we needed that 3 coming from the left-hand side. You are trying to figure out this limit right here. If you recall, the graph of that looks something like this. You have 3 minus root minus t, square root of 3 minus t. Your equation goes like this, right? So that's why we need the one-sided. We're approaching 3 from the left-hand side, we get a 0. if it is coming from the right-hand side, the limit does not exist. If it doesn't come from it either, if it's asking for both sides, then the limit doesn't exist. So we have to have it coming from the correct side. And this time coming from the left would be the correct side to give us an actual answer, because this approaches 0, right? So my final answer would be 0 plus 2 root 3. My integral answer is 2 root 3, right? Okay. This one is a little bit trickier, right? Because my asymptote is not at the end of my interval. So you have to remind yourself, where is the asymptote on this? Well, the asymptote is at x equals 3, and it's within this interval of 0 to 3. So what that means, then you got to split up your integral here. You got to go from 0 to 3 of 1 over x minus 3 squared dx, and then go from 3 to 4 of 1 over x minus 3 squared dx. So remember, your interval of 0 to 4 now got broken up to 0 to 3 and 0 to 4. So because your asymptote is right here, your asymptote is right here where the 3 is. So the first interval will be heading to 3 from the left side, and the second interval will be heading to 3 from the right-hand side. So this will be limit as t approaches 3 from the left side, 0 to t, 1 over x minus 3 squared dx. And then this one will be heading to 3 from the right-hand side, t to 4, 1 over x minus 3 squared dx. All right, so now same thing. I am going to work on this integration on the side because it's a little bit easier that way. I can see that u sub is x minus 3, du is dx. So this is really the integral u to negative 2 du. So taking the antiderivative will be u to the negative 1 over negative 1. So negative 1 over u will be my antiderivative. So it's really negative 1 over x minus 3. Okay, so now I can go ahead and plug that in. Limit as t approaches 3 from left-hand side, my antiderivative is negative 1 over x minus 3. That will get evaluated 0 to t. And then the second limit, t approaches 3 from the right-hand positive side, I get negative 1 over x minus 3. And then t to 4. Okay? All right, go ahead and plug that in. I get limit as t approaches 3 from left-hand side. Okay, I get negative 1 over t minus 3 minus a negative, so plus 1 over 0 minus 3, so negative 3. Okay, plus plugging in the 4, I get, so limit as t approaches 3 from the positive side, plug in the 4, so I get negative 1 over 4 minus 3, so 1. Okay, minus a negative, so plus 1 over t minus 3. Okay, so now again, keep in mind, you're looking at the limit of this one, right? So t minus 3. What does that typically look like? The graph of that looks something like this, where you are at 1, 2, 3. There's your asymptote, and you have a branch going down this way and a branch going up this way. All right, so why is that important? Well, the first limit says I want t coming from heading to 3, limit as t approaches 3 from the left-hand side. So coming from the left-hand side, this is going down to negative infinity. So that limit is going to be negative infinity. So negative of negative infinity minus 1/3. Okay. And then here you're minus 1. And now this one is the same graph, right? This is the same graph, but now I'm heading to 3 from the positive side, from the right-hand side. So I'm heading to 3 from the positive side. So that's going to be a positive infinity. So you have infinity minus 1/4 plus infinity. So infinity plus infinity is gigantic, minus 1/4, nobody cares. So your answer is just infinity for this one. So this is a divergent integral. Okay, so now as you can see, this is how to approach a problem like this. And basically from this point on, whenever you're given an integral, you really need to check and see if you have an asymptote in there somewhere, because if you don't check that, you will get an answer like this, right? It's incorrect because you didn't think of the fact that there is an asymptote that's in the middle of this integral. And so your answer is going to be wrong. So make sure you double check. Okay. All right. That's it.